All right, so
Hello and welcome. We should be live. Okay, awesome. I'm gonna get started then. Hello and welcome to the last networking event of the Quantum Coalition Hackathon. This has been a really exciting week, and I'm so happy to see all of the interest in the boot camp and so many names populate the Discord. As we explore the potential and possibilities of a relatively new field, it has been incredible this week to learn from the knowledge and experience of professionals and students. The aspect of the field of quantum computing that is most exciting to me is the community that is forming around it. As an aspiring physicist, I'm grateful for the opportunity to work so closely with students, teachers, and mentors from such diverse academic backgrounds. Engineering, math, physics, computer science, entrepreneurship, and other pursuits commingle in this unique space. The real spooky action at a distance is the geographic range that this hackathon has reached. We have confronted new challenges, going virtual in almost every activity, but being in contact with passionate people from many different walks of life and from all around the globe has been an irrefutable benefit. The Quantum Coalition itself, a collaboration between quantum computation organizations at Stanford and Yale, would not be possible without the ability of quantum information science to bridge impossible distances. To the sponsors, mentors, speakers, volunteers, and organizers who have devoted so much of their time and effort for months out of a hectic semester, I am grateful for your generous time and copious efforts to plan and to execute this event. So today we'll get to hear from teams who have completed the challenges, and we're going to get to hear them give insight into their thought process and the solutions that they have found to the proposed challenges. There were many amazing project submissions, and ultimately we selected presentations to showcase the diversity of the challenges and the projects, but in no way do the selections factor into the challenges or to the judging. So without further ado, welcome the first group presenting their solution to the IBM Creative Challenge.
Hey, I'm Reek, and I'm here with my friends Lou, George, and Christian, and we're really excited to show you guys what we've built for this hackathon. We call it Gorg's Grooves, the music of quantum interference. And essentially, we started with an idea, the metaphorical duality between quantum interference and sonic interference, or like the interference of sound waves. And we really wanted to explore this in an interactive way. So we wanted to build an application where the user could interact with a quantum instrument or sampler of sorts to generate an audio waveform. And the most intuitive means by which we thought this was possible was by letting the user feed in some text and getting an audio file out. And I guess the really interesting part was how we generated the audio file, but here you can see anyone can go to this link over here, gorgsmusic.hergraph.com/generate, and you can put some text in here and generate it. And that's, I guess, sort of the application aspect of the project. Yeah, so I guess next, Lou can talk about an overview of the project itself.
Hi, everybody, my name's Lou. And as Arik said, I'll just be giving a brief overview of our implementation. So the first thing we did was, you can see we have an input string here, but we used the Bernstein-Vazirani algorithm to encode the string input into Qiskit circuits. So we did a character-wise encoding. And then one of the problems that we had, or one of the things we had to decide early on, was whether we wanted to use pulse schedules or probability distributions. We ultimately decided on using pulse schedules. And we definitely we spent a lot of time during this challenge understanding the Qiskit pulse schedule library. But onto the implementation, each character has a unique circuit, which in turn generates a unique pulse schedule. We then converted these pulse schedules into waveforms, and then we superimposed them, creating an interference pattern specific to the word. So as you can assume, our input string consists of words separated by spaces, and essentially each character in the word corresponds to a waveform. The waveforms are superimposed to give a specific waveform for the word. And then what our site does, which Arik showed earlier, is we eventually convert these waveforms to audio waveforms and export them according to input order. And now I think George, Christian, and Arik will give you a little bit more insight into the actual code and implementation.
Yeah, so I guess we sort of started in a Colab notebook, and we essentially, here you can see the character Q and we encode it using Bernstein-Vazirani into an oracle, where we apply CX gates to each character onto the output channel. And then all of the characters are in superposition. And so each character is represented like this. And then when we convert it to a pulse schedule, it looks something like this. So we take this pulse schedule and we convert it to an array of complex amplitudes, and we superimpose the complex amplitudes for every contiguous character in this string. So like QCHack, we're interfering the characters, like the pulse schedules for the characters Q through K here. And so here you can sort of see we're using quantum interference to generate the oracle, right? And we're also using sonic interference to essentially combine these pulse schedules into the waveform for a single word. And then we concatenate the waveforms for each word. And that generates the ultimate output. And that's sort of the crux of the project. The last sort of thing we did was we took one of the samples that we generated from this algorithm. So here you can see if I want to test, I can just give it an input string. It gets the audio waveform from the string, and it's just a NumPy array of floating point values, and then you can hear sort of like the output from it. So if I don't know if you can really hear that, but it sounds kind of muffled. And the thing is, we have a deterministic way of processing this afterwards, but essentially you can take a look at how we did that. So first we so this is the original. So the original WAV file is what you just heard. Then we converted the WAV file to a MIDI file using an online converter, and it sounds something like this. Okay, so that there's not much. It's interesting, but I think we can do better, right? So then we quantized to 1/64th triplets and to A major pentatonic, so it sounds like this. We also scaled it up. And then we listened through the whole thing and we found some snippets that we thought were interesting, and these are the snippets that we found. And then what we did was we took those snippets and we wrote a song from the snippets. It just inspired from the melodies. And we can play the song for you now. So I guess before we do that, I'll just show that the first snippet that you heard is essentially encoded right here. If, of course, let me see if this. Oh, give me one sec. Actually, yeah, so in order to show this to you, maybe I can just show you the from the video itself, because the I don't have my hard drive connected, my external hard drive, so the instruments aren't available right now. So right here is the song itself.
Arik, I think the sound is cutting out a little.
Yeah, so you get the idea. Essentially, we inspired by the snippet, we made this song, and yeah, I think we really just wanted to draw out on the metaphor between quantum interference and sonic interference, and just sort of the beautiful way in which the two worlds collided. Yeah, so that was essentially our project, and we hope you enjoyed it.
Guys, thank you so much for that wonderful presentation. That was so cool. Never would have occurred to me to do something like that. That was really interesting. Okay, now welcome the next group, who's going to be presenting their project for the Microsoft Challenge.
Hey, can you guys hear me right now? I'm going to imagine, so I think I saw the closed captioning there. But yeah, thanks for having us on. My name is Sean Gailey. I'm with one of my group members, Zenrong Yap, if you want to just say hello real quick, Zen.
Hey, everyone.
Yeah, so our other two teammates are here with us in spirit, so their pictures are up here on the slide. Yeah, so we did the Microsoft, we implemented the Microsoft Challenge, which really builds up to solving a interesting problem using Grovers. And yeah, so can I see the next slide, please, then? Okay, so this challenge primarily, as I said, focused around building up to solving an interesting Grover search problem. So just to quickly go over the algorithm very briefly. So it uses an oracle to mark the truth of our input state, flips the oracle that we're searching for, uses something called a diffuser, which flips around the average. And then if you repeat this process over and over again, it allows us to achieve the result we're looking for at a much faster rate than the classical analog. And so certainly for us, the biggest challenge we found with implementing a Grover search was designing an elegant oracle that achieves our goals. So part one of this task, there were two parts to this. The first part was a great primer for designing oracles. So I'll briefly touch on what we did for this part. So next slide, if you will, Zen. Awesome. All right, so in these problems, we implemented we were doing various gate synthesis problems. We were trying to design a useful output circuit. So for example, like the very first problem was devise a marking oracle that divides a number by 4, right? That determines if a number is divisible by 4 or not. Now, we definitely spent more hours than we would like to admit trying to figure out how to properly implement oracles. But once we got the first one done, the ball kind of began rolling. And we noticed that part of the difficulty was coming up with an intuition for the logic of why something has to be correct. So just as an example, take the first task with divisibility by 4, right? When trying to come up with a logical rule that will consistently return the result we want, in this case, we noticed that the least 2 significant bits of the binary representation of the number or the state could be used to reveal divisibility by 4. And that was just something we noticed upon inspection of just binary numbers. And so we kind of used that general intuition to bootstrap our way into a general solution. So we have a snippet of our code up there. And that was generally the theme for the remaining task as well, in which we identified a certain intuition for the problem, for what our oracle is supposed to be doing, and work from that intuition. And so this is what kind of gave us the requisite, I guess you could say, background into actually being able to implement an interesting Grover's problem. So I'm going to pass it off to my teammates then to discuss a little bit about the next part of this challenge.
Okay, so for part 2, we were looking at trying to find an interesting problem and trying to solve it using Grover search. So we were brainstorming and we had a few ideas. There was finding a route for an electric vehicle and like lots of them together, finding orbital paths for rocket spacecrafts, But then we felt that we wanted to do something that was even more like world changing, something that would change people's lives. So Sean and I are proud to announce our idea, Quantum Tinder, using the Grover's algorithm to find the best match for you. Best thing, the Tinder, OkCupid, Bumble, or Coffee Meets Bagel. So first, you have to initialize the database with all the people and all their characteristics and preferences. So if you look here, Sean is 96 inches tall. His eye color is kingly purple, he's 20, and his street cred is an engineering physics student. For me, I'm 1.8 nautical miles, eye color gold, street cred, you know. So, and then we have to have our preferences, right? So on the left, we keep Sean's characteristics, and on the right, we have my preferences. Right, my age preference is an even number. Thankfully, Sean fits that. So then we create an oracle that fits my preferences to his characteristics, and vice versa. So given that that Sean fits my preferences, we initialize ones for all the dimensions that we can vary get along. And we use XOR and XGates to check each clause. And because each clause is either just a range or a quality to value, it's quite easy to check that. And if all clauses are met, you store one as the output qubit. So that would be when the oracle outputs a 1. And for the code snippets, we have here that we initialize the qubits. The input qubits would be the preferences for each person. And then we have the output qubit that we're controlling, right? And we plug into the oracle, and then we apply Grover search along there, and everything just gets taken care of. Sean, do you want to add anything?
Yeah, thanks, Zen. I think the only thing that I'd add there is to notice that the only way in which we'll achieve a match at the end of it is if all of our preferences are matched with the associated characteristics of the potential matcher. So when we're comparing the preferences of one person compared to the characteristics of another, the only way we're going to return 1 in the end is if we have a perfect match. And if there's rules that don't match, so let's say my height preferences is 180 centimeters or above, and someone else's characteristic is that they're 170 centimeters, then that's going to return false for that rule, and that will essentially remove the possibility of being a match in that case. So that's sort of the technical intuition of what we're trying to do. And yeah, so that's our idea of Quantum Tinder, which will speed up the rate of matchmaking. And that was our little solution for the Microsoft challenge. And yeah, thanks a lot for the chance to present.
Thank you very much.
Yeah, thank you guys so much for the really thorough explanation of like such an awesome idea. Wow. All right. Our next group is going to be sharing their solution to the Quantum Coalition Hack and Yale Quantum Institute Collaboration Non-Technical Challenge.
Hello. I think it's our turn. Nisha, are you here? Yeah, thank you. Thank you so much, everyone. And basically, I'm a team member of Cookie Phoenix. My name is Parv Agrawal, and my teammates are Amol, Mahsukar, Daniel Salazar, Rosie Banerjee, and Nisha Banerjee. And basically, our part of field like on where we use this our quantum quantum theory and quantum computing is like logistics, and like most of the part which we are like going on is completely based on our logistics and everything, like how to ship, how everything ships around the world, how everything like goes from here and there, like how they get connected and like that. And to make that thing optimized and like more smoother than previous ones, we just come with a new kind of idea. And about that, my friend Daniel will let you know more about it. Daniel, are you here?
Yeah, yeah. Can you hear me?
Yes.
Hello, can you hear me?
Yes, Daniel, we can.
Perfect. Perfect. Well, we are going to address this case from a perspective of an international trading company, actually as a transportation company that's in part of the international trading part. We are going to explain this as we were sharing, like we were trying to tell to our boss, we're in this company that's a transportation company. It's on the it transports many kind of heavy cargo, and we're trying to tell to our boss how to actually manage the quantum revolution, quantum technology, in order to apply it to our company. And this is what we've been discussing. About our company. We are in the transportation industry, and we send the cargo from one warehouse to another. We move from shipping ports to warehouses to different places. And we are talking about a company that has more than 20 years experience implementing different solutions in order to get that edge in this field, to gain more efficiency, to win some time. And those little efficiencies we get to extract from all that new technology we get to use are really important in order to achieve more capabilities, more market participation, and differentiation. So that's the way our company works. And the challenges we have to face are mainly two big challenges, which are optimization and still prevention and protection. Of course, there are many others, but these two are the most important and challenging ones, and the ones who has the most impact over profitability. And also, they can be taken by quantum computer in the future, and also we have some little applications right now. And in the case of optimization, we have to do many things. For example, in operations, acceptance, and assignment, sometimes, actually very often, it happens that we reach the top of our capacity when we cannot give any more operations to our customers. So we have to use the current cars we already have, the current technology, the current different things we have, in order to accommodate the best way all of those requirements for making the best of it. For example, we need to examine the routes, which of the routes are the best for doing it in the least time amounts possible, and trying to incur in the less expenses possible. For example, we have to measure the road qualities, how many tolls will be on the road, and what's going to be its cost, the distance, and all that. We have to worry about the distribution and accommodation of the cargo inside the truck, and that has to do a lot with how you actually can deliver the goods in a proper way. It has to be optimized as well. Fuel consumption is one of the biggest expenses we have in this industry, and the parts life cycle, it's also very important, and it's not so neatly done. And if you actually don't do it well, you get some extra expenses that would have avoid otherwise. And well, materials implementation and provisioning, and the best response to an emergency is also very important, because you have to be able to take the best option to rearrange any schedule in order to fit it the best way possible when it happens that you have an emergency. All that has to do with optimization. Now, with still prevention and protection, it has more to do with information traveling from one place to another. In this time, we are using a lot of artificial intelligence and blockchain, and even that blockchain is very strong for protection matters. If we don't get into this new technology, this quantum technology, we might get to a point where that blockchain won't even be useful to safeguard our data. Okay, and the relevance of this industry, for this quantum computing technology for our industry, is precisely addressing all of what I was mentioned before. For example, dynamic route optimization. We could just introducing some parameters and extracting information from many different sensors along the internet, which are located in strategic points. We can gather information and unite that in the dynamic route optimization. And the quantum computing is important here because it gets very high computation needs. It needs a very high computation capacity in very few times. So this is a very important thing to address. It makes us boost resilience and much more. And now, who are part of the quantum computing ecosystem? I will talk a little bit about this. It's before going with Parf. Well, we have big names in the industry that are taking part. We have, for example, BMW. We have Anthropical Labs. We have Microsoft, IBM, and all of them are researching, and we could be part of their research associates. We can unite into collaboration in order to develop all these things that might help into our company, into our field. And by being one of the first to develop and implement this, we would grasp a greater capacity in order to differentiate and be apt for the challenge of the new era. Now I will give a pass to Parf in order to keep with the presentation. Thank you.
Thank you so much, Daniel. So now my part is, why should we act now on these kind of things? See, as most of the statistical data that is present on various public domains pointing towards a condition termed as quantum supremacy in very near future. It will create an enormous hype and like a very good will in the market of developed economies like of USA, Germany, Europe, and also in various large emerging markets such as India to like invest in these kind of future technologies of quantum computing. This ensures the future of the company, which is investing its resources and funds in developing a chain and a workforce ready for the QC revolution, or you can say quantum computing revolution. The company will take advantage of the progress done by well-known researchers in the field of like quantum communication, quantum machine learning, and simulation, and everything like which is related to these kind of things or something. And like in order of merging and making the best profit out of it. With time, the company will also think of providing the route handling services, transportation, and like all kind of logistic services on highly optimized grounds, as well as on as more secured and newer technologies at much cheaper price as compared to their competitors like DHL or FedEx companies, etc. Now, other slide is about our analysis of QC strengths using SWOT. So basically in that, we will see like the strengths of it might be it is a kind of very highly collaborative field. Like we can see like many big companies are collaborating with each other to like get some fruit out of it. And like it's also been on the table of our governments, and like government is also funding a lot to these kind of you know like in these kind of projects, open projects and everything. And it's all like it's all about opportunities too. Like we can find many opportunities in these fields. Like it is making a new kind of market in the field, and like it's a highly profitable field. Right now it's not that much applicable, but yeah, with time being, it will be the most highly profitable market making field. And after that, it contains a high optimizations levels and like high data security and everything. So basically, yeah, it's all kind of an analysis in this slide. And after that, it's all about like conclusion, like what we conclude from our whole journey about like what we are going and why we are taking this thing. And like it's all about like we all are present in the world where we are like going from a classical computing to a shift of quantum computing. And it's like making our logistic services as well as trading services, the quantum computing, they also get like harnessed from these kind of things, or like these revolutions, they also should be the part of this revolution. And or like for making that, we have faced this idea. And to be honest, for like particular me, why I'm so much interested in this idea is like the thing which fascinates me the most about this idea is like it will be the first of its kind in this field, and we have the chance to become a path leader in this field. And that will work a lot in the favor of company as well as in the favor of the quantum revolution, which will definitely come in 3 or 4 years or so, yeah, in the line. So with that well note, I think that will be our team. Thank you.
All right, thank you so much for sharing that wonderful presentation with us. We will have one more presentation followed by a 10-minute break, and then we'll get to the next round. All right, now let's move to the next group who will be presenting on the Google Quantum AI Challenge.
One second. Could you hear me?
Yes.
Excellent. Okay. Today I'm presenting for the Google Quantum AI Challenge. The gist of the challenge is to develop a transpiler for the Sycamore quantum computer. A transpiler is a device that takes a quantum circuit you give and then maps it to some specific architecture. But the challenge has a twist, which is the initial condition given to you is not really a list of gates, but instead it's a unitary matrix. So the task here is twofold. The first is, how can we decompose this unitary matrix into a series of quantum gates? And the second is, how can we map those quantum gates onto a physical machine? So let me share what I've worked on for the past 24 hours. It's a sort of a optimization and decomposition scheme that's built on a bunch of different libraries. It also includes some of my original. So let's start from the very beginning. We know that the input is a unitary matrix that's 2 to the n by 2 to the n. In general, the decomposition of a unitary matrix is difficult. And as you might have seen from the judging code, the lower bound is exponentially n, where n is the number of qubits. However, if you look at the test case, there are a bunch of examples that are not really that difficult compared to a random unitary matrix. So first of all, we need to get the identities out of the way because they have no action per se on the actual quantum state. So for the identity, we just generated an empty barcode. And then there are two special classes here. They are the incrementer and the diagonal. Both cases can be solved with a polynomial number of gates. And for them, respectively, we use both Qiskit libraries. The first is the MCX gate, and the second is the diagonal. And afterward, we just called a native decomposition function to obtain a list of a polynomial number. Now, the most difficult part here is the random matrix. I looked at a bunch of options and I decided on using the OpenQL decompose function that implements the recursive quantum channel decomposition, also known as recursive QSD, which is an extension of the recursive cosine sine decomposition, that is the recursive CSD. So right now we've discussed by cases and figured out what each part of different matrices would be decomposed to. Afterward, when we obtain a list of gates, we start the optimization, which is, in my opinion, the more exciting part of the project. So in the optimization stage, we have two inputs. The first input is the decomposed circuit that we obtained from the previous round. And the second is the bunch of qubits that we have also as an input. So there are a lot of different options around, and it's probably a little bit difficult to tell which one is the best for some arbitrary unitary. In this case, we use the power parallelization because if you recall, Bolin said the test machine would have 16 virtual CPUs. Right now, although there are 5 boxes here in the actual code, because of some selection criteria, there will be at most 3 workers running. So there are a few options we can target. The first is to target the Sycamore gate set plus topology. That is to say, our list of gates, when it's turned into a circuit, will be natively possible to execute on the Sycamore quantum computer. The second option is a little bit weaker, which is to target the Sycamore gate set while neglecting. And the next few things are, well, this one is kind of important. It's just to target the standard transpose. You can just come up with something like Rx, Ry, Rz, and as well as a multi-qubit gate like C0 that would constitute a universal gate set. The following two are sort of, it's kind of exploitative of how the problem is framed. We recall that the goal of the decomposition is to turn this large unitary matrix into unitary matrices or gates that are representable on 2 qubits. So if you recall, the CERC library provides an custom method for designing an arbitrary gate with a custom unitary matrix. In this case, we can start from the optimization result and start to recombine gates into 4x4 unitary. That is our custom designed 2-qubit gates. To do this, it sort of involves some sort of dependency analysis, but it's a lot easier than the classical scenario. You just need to look down the circuit and identify the pairs of qubits that are interacting, and identify regions where only these two interact. Instead of one of the qubits having an interaction with some third qubit in the middle of the region. So after you collected all of those regions, you can reassemble each region into a unitary matrix. You evaluate its effect on the circuit in the unitary form, and then you add a custom gate to neatly wrap it up. So that could save us a lot of when it comes to arbitrary unitary matrices. And for empirical conclusion here, a preliminary observation is it saves around 25% in the metric of total multi-qubit gate count. Now, the same idea can be applied to the small unitary direct expression, which is small 1 or 2 qubit unitaries. So, well, this is where I guess the value of parallelization comes in. You can both try to target the Sycamore gate set of topology and get these extra points, or you can try a direct expression of 1 and 2 unitary matrices. Well, I guess for 1, you can always target the Sycamore. But for 2x2 unitaries, sometimes you will get above the theoretical lower bound. So this is why we execute these all at the same time and then pick and choose which one is the best. For scoring, we just imported the code that's used in the judge library and defined criteria for selecting one result over the other. So I guess that is overall how the structure of my code looks like. It's separated into 3 files in actual implementation. It might be a little bit hard to see, but the solution here is the entrance to all of the cases, and then we start from here. Ask these 4 questions to separate them into 4 cases. And then we perform their respective decomposition via things like here, like incremental decompose, diagonal decompose, random decompose, and there are a bunch of other helpful. Now, I guess before we conclude, we can talk a little bit about the results. The result is pretty good. I get 7,653 over 8,600 points. And the main places where points were lost are for random large unitary matrices. It's pretty much a certainty that you're going to do worse than the theoretical bound. But based on prior work with QSD from other authors, the typical bound is usually around 100% higher than the optimal theoretical lower bound. And in this implementation, due to some other plethora of optimization, it's a little bit better than that. Usually, it's around 70 to 80% higher than the theoretical bound. So yeah, overall, I'm pretty satisfied with how things have turned out. It sort of looks like a pretty neat workflow of how you can deal with general unitary matrices. And going forward, I guess one thing that I want to work on is to add some variational ancilla. Well, you can't call it ancilla if it's appended at the bottom of it. But to add a couple of single or short multi-qubit interactions at the end of the unitary to act as a corrective term to further reduce the diamond norm between the sample and the actual output. So yeah, that's what my project is about, and it's overall a very fun exercise in understanding decomposition and transpilation, and also just working with all the caveats. So yeah, that's it. Thank you so much.
That was an amazing presentation. Thank you. I really want to express my appreciation for all the groups who have presented so far, and for the rest of the groups who will present after the break. Now we will briefly adjourn for a 10-minute hiatus. There will also be an informal Q&A session, so feel free to ask questions to groups who have just presented in the Twitch. We will return here at 2:05 p.m. Eastern. Thank you, and I'll see you.
All right, welcome back from the break. And next up on our order of presentations are the IBM Technical Challenge, the second one. Feel free to share screen when you're ready.
Okay. Can you see my screen?
Yep, looks good to me.
Okay. Hi, everyone. My name is Ming, and I'm here to present our work in the past 24 hours about the IBM Technical Challenge that we try to implement the QDIS gate and with the QCHack pulse. And these are my teammates and me. And so the motivation of this work is that by accessing the higher energy states, we can do some operations beyond the conventional qubits that use only the two-level systems. Also, the qubit here, we mean that if you have consider the harmonic oscillator in the transpose systems, that you could have several higher energy states that you encounter, for example, like the number of energy levels, and then you can do more operations with these systems. Like you can form the energy levels 0, 1, 2, and D, and you can also perform the unitary operations that is a D-dimensional. For example, like in this work, we are trying to implement the cyclic shift operations in this qubit system. And we also try to use the QCHack pulse to implement the action of the operator. So the challenge we face with this IBM Technical Challenge is that there's a limited time here, and also the resource on the cloud is actually very limited, that we can only successfully run on the actual backend RMonk, and the other fake backends were not really working properly with Pulse. So also the 0, 1, 2 state discrimination is very difficult, that sometimes you get a very noisy result or etc. So to build a very adaptable class of the QDIS gates operation is actually not very realistic. So we want to focus on the 3-level QTRIT case that is using the existing pulse instruction. So the first step before you do any higher energy state operation in the QCHack states, you need to calibrate all the corresponding frequency transition frequencies, such as 0 to 1 state and 1 to 2 states. So the graph here is showing that you have to do the frequency sweep near the peak of the frequency omega 1 to 2 state, and then we found the very accurate calibrations before we performed the calibration of the frequency and the pi pulse amplitude before we perform any gate operations. And that is important to have a lower noise and lower error result. So here's the example of like the results from the top right figures. That's how the 0, 1, 2 states are demonstrated in the IQ plots. That you can see that there are 3 groups of clouds that's centered by the mean values of each state with the black dots. And we try to use the different machine learning classifiers like LDA and QDA or the MLP to trying to benchmarking which is the best classifier that gives us the higher score. And it turns out that the neural network with 2 hidden layers of like 100 and 100 neurons, that will give us a higher score about 0.84. So we hope to stick with that to further analyze our the measurements later. So in addition to the QCHack pulse calibration, we also do the primary gate operations that we built out a class called QCHack, and that supports different unitary transformations. For example, like the cyclic shift that perform the amplitude shift that all the amplitude will shift from the right cyclic, and then also the reverse shift of acyclic shift. And also we add the two states, X gates, like an amplitude swap between either two states, and also the two-state Hadamard gates. That's what we have so far. This is the example of how we illustrate these operations with the QCHack post schedule instructions. Yeah. So after we have the discriminators tested, we try to apply it on our QDIP gate operations. We use a cyclic shift to test that on the 0 states. And so with the 0 states that you expect to have the state vector to be 1, 0, 0 as the initial state. So after a cyclic shift, you will expect to see a result to be 0, 1, 0. And then that would be, you will expect that you will measure the states most likely in the 1 state. But however, when we apply our best classifier, NLP, it results to some very different states that the IQ plots seem to be shifted like away from where the classifier plots are. So it results in a very different result. But for the LPA classifier results, it's actually, although it's shifted, but it gives you a very perfect prediction of 1 state. But for this part, we are not very confident about this result. So more works need to be done to optimize our discriminators. So the future work is to improve the discriminations of these future states, and also maybe further benchmarking all the errors, and also T1 and T2 states, and maybe even implement the multi-pole QTRIT states like a control knot version, the QTRIT version of control knots, etc. And we also noticed that because it's a 3-dimensional unitary transformation, it's very natural way to simulate the spin dynamics in the spin 1 system that in the high energy physics applications. We also hope to, if we have time, we can extend it to the system with D larger than 3 state systems, that if the hardware limit of current transform qubits are allowed. Yeah, you can see more results in our GitHub link. And here we want to thank all the organizers of this event and all the participating companies, especially IBM, to provide the hardware and also the software, QCHack and QCHack. Yeah, thank you.
All right, and thank you for that interesting and well-documented benchmarking project, and well done working through all the difficulties. So our next group up will be sharing their solution on the QBraid challenge. So feel free to share. So it looks like the QBraid team is having some Zoom troubles at the moment. So is the Google Quantum AI Challenge team ready to present?
Oh, okay. Hey, I'm here. Yes, I can start. Just give me a moment. Yeah, hopefully you can now see my screen.
Yep, you're good.
Oh, great. Hello, everyone. So my name is Wei, and so I'm going to talk about the project I have been working on in the past 24 hours toward the Google challenge. So the challenge, as the previous speaker Alan already mentioned, is to compile an arbitrary quantum circuit to a NISQ device. And in this challenge, we are working on the Google Sycamore device, which has 54 qubits in total. As shown on the left, you can see these 54 qubits, they are connected like in this 2D topology, and only adjacent qubits are connected. And only 1 qubit or 2 qubit gates are allowed on this hardware. So in order to run interesting algorithm on this device, like one key challenge is that we need to compile this quantum circuit to the operations that are supported by this practical quantum hardware. Formally speaking, for an n-qubit device, the Hilbert space is of dimension 2 to the n. And any arbitrary quantum circuit can then be expressed by a 2n by 2n unitary matrix. Then the outcome of this project is to provide a function that accepts an input of this 2n by 2n matrix, and then that outputs a list of operations that can be passed onto this device. Okay, so yeah, as I just mentioned, there are two challenges on this hardware. So first is it only accepts 1 qubit and 2 qubit gates, and only some specific types of 1 qubit, 2 qubit gates are allowed. So if we encounter those popular C0 gates, we need to somehow convert them to these native gates that can run on Sycamore. And also not all qubit, we need to kind of, if we want to use ancillary qubits, we can only use those qubits that are next to the qubits in the circuit. And in this challenge, because time is really limited, then the maximum number of qubits involved is 8. So ideally, we probably can work with more qubits, but time is limited, so we didn't have time to do more qubits than that. So here I want to briefly talk about the logic flow when trying to solve this problem. So first, we started from the simplest case. The very simple case is if it is a simple identity matrix. If that is the case, then we don't need to do any operation on the circuit. It's just by itself. And then the next simplest things are if they are single qubit or 2 qubit or 3 qubit matrices. And because these are simple because CERC already provides solutions to them as I put on these snapshots. There is this single qubit matrix to phase X, phase Z, or a 2 qubit matrix to operations and 3 qubit matrix. So these are already very nicely in the CERC library. So we can just use it. But one thing we need to do is that we need to further convert these operations to the Sycamore gates because some operations do not work on Sycamore. Then the second step is to determine if the input matrix is a diagonal matrix. And this is also kind of simple because so first is that it's also there's already a solution in CERC, and we only need to convert the input matrix into the corresponding diagonal angles in radians, so that it can be automatically converted into a diagonal gate. And then most of my time I spent was to working on this incremental matrix as in step 3. And step 4 is the most difficult. So yeah, I think the previous Google present already present a lot great on the step 4. So I will mainly talk about step 3 here. So here is what an incremental matrix looks like on the left. As you can see, there are a line of ones that is away from the diagonal, and there's another one on the right upper corner. So we actually can make use of this unique structure to make the compilation much easier. So let's first understand what this incremental matrix is doing. So this is a 3-qubit incrementer. So if we apply it to an arbitrary, not arbitrary, to a state in the computational basis, say all zeros, then what it does is that it will just increase 1 digit, like the last digit. And then if we apply the matrix again, then it will just go to the next digit. Then it just kind of the number just it just goes through this all the states in the computational basis one by one. So in practice, this can be used as a counter. So this is a very useful matrix, and this also provides us a way to kind of have a way to compile it much easier, because we can just we only need to flip the qubit, like the higher qubit only when all its previous qubits are 1. Say like if you can see my mouse, so if we want to go from this state to that state, then we only flip this qubit only when like its 2 previous qubits are 1. So this is just the multi-controlled X gate. And very nicely, this multi-controlled X gate can be decomposed with an existing like a function in the circ library. So this is basically like how incremental matrix was solved. So yeah, and the random unitary matrices. So actually, I didn't really have enough time to complete a random unitary matrix solution. But if you are kind of more interested, I want to just point out the two references I have been reading and find them that can be very useful, and I'm hoping to actually continue working on this even after the hackathon. So basically, I found that there's this kind of mathematical-based software. It already very nicely convert a universal matrix to operations, and this is based on a theory paper like in PRA back in 2016. But because like it's all written in Mathematica, I was spending there's a lot of time involved trying to convert these things to Python, so I didn't get time to complete it. But overall, I think I really enjoyed this hackathon, and I really also like playing around with the circ library, and also kind of appreciate how powerful it is. And yeah, that's it. Thank you very much.
Yeah, wow, thank you for such an amazing presentation on, especially with all the time crunch of the hackathon. Next up, we'll have the Microsoft Challenge group go, and then I think Cube is here, so they'll go after.
Hey everyone. So we are a team of 5 Caltech physics majors who worked on the Microsoft Quantum Challenge. As you heard earlier, it mainly involves coming up with code in Q# and coming up with ideas in Q# that could implement Grover's algorithm. So we're gonna quickly get into like part 1 of what we did. Next slide, please. So part one involved like various tasks where we had to figure out algorithms or just code snippets that can do several different tasks. The first one was say disability by 4, where we were given a binary number in little endian form. Little endian basically means that the least significant bit, the bit that means 1 would come first, and then it would go like 1, 2, 4, and so on. To check divisibility by 4, what our team noticed was all you need to do is check whether the first 2 bits are 0 or not. For that, the easiest way we found was to flip the first 2 bits and have a controlled flip from the first 2 bits onto the target bit, so that only the target bit is only flipped to 1, which is the accept state, when the first 2 bits are 0. So we got that done. Next slide, please. Next slide. Yeah, thanks. For the second and the third task, the problem was the same, but the way we implemented it was slightly different. I guess like, we were restricted in task 3 to not use larger qubit gates, which could make sense if you think about how these are actually like the hardware is built. For tasks, so the question was whether all 3 bits are the same or not, or rather the question was it's converse, like are at least 2 bits different. What we noticed was we only need to flip like each bit separately. And if there were if there were like 2 1s in the bits and 1 0 in the bits, then we'll have all 3 1 bits, which we could use to get the target to be set to 1, and doing a very similar thing for when there are 2 zeros and 1 1. That was our idea for task 2. And the next slide has the code, if you can go to that. This basically involves flipping the input back and doing a controlled gate in between. If you can go to the next slide. For task 3, we had to do the same thing, but not use any qubit gates that would use like 4 input bits. We came up with this method of doing it, which involves basically encoding. So we'll have to basically leave out one of the qubits, and we cannot have it interact directly with the target bit. So we encoded that information from that 1 qubit into the other 2 qubits, and then enforced a condition from that to the output, and it ended up working. This took us a while, like an hour or so, but it did work. For task 4, I'm gonna hand it off to Anand.
Yeah, so the idea for task 4 is essentially it's the same as task 3. So the task is to determine if a graph coloring has a triangle where all 3 edges have the same color. So the first step would be to find all triangles, and this can just be done classically. You iterate over all possible edge triplets, that's O of n cubed, but you can reduce that with some smart programming. The second step is that for each triangle, you simply run the oracle from task 3, because if we notice when all 3 edges have the same parity, that's identical to all 3 bits being the same in task 3, and similarly when they have different parities. So that's the idea behind task 4, and we can run this in a way that's consistent with the specifications without significant modification. But we didn't have time to code this up, but yeah, this is the idea. And I'll hand this off to the next presenter.
So deviating a bit, so all right, let me new share. Oh, bear with me a second. Wait. Oh, very sorry. There is a paper I wish to show you guys, but the Zoom selection is blocking me. Give me a second. Okay, yeah. Okay, here we go. So sorry for the delay, but essentially, so our basis for what we are we didn't have time to fully flesh it out for a task for the second part of the project for Microsoft, but it's based on some previous work Shub and our other teammate Helena did in the previous class, which is Hamiltonian, compiling a simulation circuit for a Hamiltonian using random sampling. And basically the backbone of this is taking a Hamiltonian for a physical system. In this case, I believe it's for a simple hydrogen atom for the energy levels, and then taking the decomposed version into qubit gates and finding a way to compile a simulation circuit using random sampling. And we compare this to other methods such as a Char-Suzuki decomposition, which is typically used, which is one of the first formulated ways to do this Hamiltonian simulation circuit compilation. And what we found is, the number of gates used to get a similar level precision between this Q-drift random sampling implementation of the Hamiltonian versus the standard Char-Suzuki decompositions scales much better with in terms of number of gates. And we have these are short description of number of tests. We didn't have time to compile slides for this, sadly, but essentially here we can see some results for a similar level of precision, how the gate count scales and you can see that although at first the random sampling does much worse for if we don't want for low precision, as we go to higher precision, then it does much better than the first order Trotter methods. And this can be seen through other metrics as well, such as this is using timing of this is number of gates. This is using precision, another type of comparison. This is using a time metric to compare the two methods. And we can use this in the subsequent part, I think Aditi is going to talk about, to construct an oracle to get some interesting physical results for a certain system. So let me share again the slides. And yeah. All right.
Yeah, so we're all physics majors, so we're all interested in condensed matter systems. And one of the, in condensed matter, there are a lot of models that exist to basically model electrons and positions of nuclei and all these functional electronic materials. So an example of this would be the independent electron model. So if you're given a condensed matter system with a fixed set of positions of nuclei with electrons, you get this Hamiltonian. And the second, as you can see, there are two terms in this Hamiltonian, and the last term, the electron Coulomb interaction, makes this a many-body Schrodinger equation, which makes it extremely difficult to solve. So a lot of these models, like the independent electron model, they come up with approximations, like to replace the Hamiltonian by an effective independent particle Hamiltonian, or to replace V effective by a constant. But in many cases, for a lot of materials, you might not want to make these approximations, and also solving the many-body Schrodinger equation, like you have to use like Hart-Proctory approximations and things like that. So what we decided to do, so if you go to the next slide. Yeah, so there's many other models like the super simple independent particle model, but yeah, the next slide. So what we decided to do was use Grover's algorithm. So instead of directly solving the many-body Schrodinger equation, if you, for example, have a Hamiltonian, which Luca talked about, we can simulate a Hamiltonian using our previous results. If we have a set of initial possible states of the system, for example, the position of nuclei within electrons in a condensed matter system. So if we can already have a guess of like possible states using something like a Born-Oppenheimer approximation, what we can do is, given our Hamiltonian, we can use Grover's algorithm and conduct a search backwards into all the possible set of solutions or states of the system that can solve this Hamiltonian and get a certain band structure. So that's basically what we thought we could use Grover's algorithm plus our simulated Hamiltonian to do, instead of directly solving this really hard many-body Schrodinger equation or just attacking it by itself. So yeah.
I believe that's it. Thank you for listening.
Oh yeah, well done, especially on such an interesting project and great work solving all the tasks. So next up, we'll have the group who did the QBraid challenge present.
Hello.
Hey.
Hey. So hello everyone. I'll just share my screen first. Okay. So hello everyone. We are Team Superposed. We are a group of 3 computer science students, computer science enthusiasts from IIT Delhi. So we'll present to you the project we did using QBraid. So the project we will demonstrate today is a digit classification algorithm using VQC. So first, let us focus on the problem statement which we are about to solve. So the problem which we aim to solve today is digit classification. It's a well-known problem in machine learning. So it's a first step of text recognition. So instead of categorizing alphabets and total paragraphs, we begin with taking a small image as an input. In our case, a 28 cross 28 pixel, which has a digit written on it. So in this case, for instance, these are the some of the examples we took from the MNSIT dataset. So our inputs will be provided in this fashion. So what we aim to do is we created a UI for this. So we will input the digit in that UI, and after selecting some backend, then or a simulator, we will run our algorithm on it, and it will display the digit after it. So since this problem can currently be solved using classical methods, we'll focus on that first. So many classical algorithms, machine learning algorithms exist to solve these problems, which can achieve significant accuracy. Since it's a small problem, existing ML algorithms perform exceedingly well and also perform quite well as in terms of time as well as accuracy. So for instance, CNNs can solve this problem very easily. However, for larger algorithms where we have a lot of size of data sets, a main problem with CNNs and other such algorithms is that having a large number of parameters, the computation of the model and also the training of the model as well as the classification becomes computationally extremely expensive, as the complexity of the algorithm and the number of features and the number of the size of the data set increases. Hence, what happens is mostly that they take quite a large amount of time to make it practically infeasible to use in practical scenarios. So we have to come with approximation. So in order to make up the time less, we are compromising on the accuracy. So for the current purpose, we aim to use a quantum model. So why we did that? So in the current scenario, we know that quantum algorithms do have a significant benefit in terms of time efficiency, but they're not quite there yet in terms of memory usage. However, we believe that the future belongs to the confluence of both quantum and machine learning. Hence, we use this opportunity to build a model of machine learning using quantum methods, QML, that is to say. So what is the advantage of quantum in this? Using superposition and controllable entanglement states in quantum mechanics, quantum computation, we can attempt to gain an exponential speedups in known algorithms which can be performed classically. A very good example of that is the Shor's algorithm, which has already been discussed at length before. So in the modern viewpoint, these quantum computers can be used and trained very like neural networks as we do classically. For instance, a trained circuit can be used to classify the contents of images by encoding the image into the physical state of the device and then performing some gates and operations on it, and then finally taking the measurements. So that is the aim of this. And so I'll just explain briefly on the state. I just also mentioned about the UI. So we have a basic UI for this. We have a drawing pad, which we used Jupyter widgets for that. And what we did was in a Jupyter notebook, we used a canvas. So when you activate that code, you can draw a character on it with your mouse. And after that, when you run the code following it, what happens, the canvas will return the coordinates of the points that were drawn. These are then processed. And then after some image manipulations, they are converted into an NumPy array as an image. And then we send it to the pre-processing stage. For the preprocessor, we use uniform manifold approximation and projection of dimension reduction for reducing the size of the input features, because we need finally a 28 by 28 image, and this what image we provided, that would be about 500 cross 250. So we apply the various transformations to bring it down to the appropriate level for carrying out our quantum model to train first the model to it, and then predict the images according to it. So next we have the QML workflow, which Pranjal will demonstrate now.
Yeah, hey. So basically the QML workflow. So basically what a quantum machine learning algorithm would do is it would take in some parameters like a classical algorithm, and it would train it. And then we will perform with those learned parameters. We will predict the output of the test cases. So basically those learned parameters are like what rotation angles the gate should be, what all gates should be in the model, and all those stuff. So next slide, please. Yeah, so this is the like what all steps are there in this quantum algorithm that we have used. So first of all, like the data we have is a classical data. So we have an image, so that is 28 cross 28 pixels. So we need to map it to a quantum state. So we use a feature map for that. So basically what a feature map does is it takes in the input vector, and then using some gates and some entanglement, it creates a superposition, and we encode that data in the qubits, the states of the qubit. So that's the first step. Then we have a model circuit. So basically these has a parameters. So like I will talk about it later, variational circuits. So these have some parameters, and using some optimizer, we are trying to tweak these parameters in order to get a good accuracy on the trained set. And so what these circuits do is like we will get some outputs. So we will do some measurements on the final state of the qubits, and based on these measurements, we will decide like how to tweak the parameter based using those optimizers. So next slide, please. So yeah, so like we try to optimize the parameters so as to reduce the loss. And next slide, please. So for the optimizer, we use the Cobila optimizer. This is like a kind of standard provided by the QCHack library. So it constructs successive linear approximation of the loss function and constraints via a simplex of interest points in n dimensions. So that's the optimizer. Next slide, please. So the algorithm that I was talking about is the variational quantum classifier. So basically a quantum neural network can be like thought of a quantum circuit, like I said before, with trainable parameters. So like what we are trying to do is we are trying to tweak these parameters, and these parameters are qubit rotations, and then we do the measurement of the circuit, and like how good the measurements are, like how much ones and zeros we are getting. Accordingly, we try to maximize them. So next slide, please. So the problem with these quantum classifiers is that these are binary classifiers, the model that we have used. So, but we have to do a 10 class classification. So what we do is we divide it into steps. So like there are multiple approaches for this. We adopted this approach. So what we do is like we have digits 0 to 9. We first classify it, either it belongs to the set A, that is 0, 3, 5, 6, 8, because these look similar, or 1, 2, 4, 7, 9. So depending on what the model classifies, so all of these models are trained independently, and then finally they are combined like an ensemble model. So like suppose I have given the input 5. So what it will do is it would it should predict that it belongs to the set 0, 3, 5, 6, 8. And then we will run another model, and then it should predict that it belongs to 0, 5, 6. And then we will run another model which will tell that yes, this is 5. So yeah, this has some caveats, like because repeated use of model, we are decreasing the accuracy, but since of the constraint that we can only build binary classifiers using this algorithm, we had to do something like this. Next slide, please. So now what a variational quantum classifier is actually, so basically there are these 4 steps. We apply the feature map. So the feature map, as I said before, is basically it takes in the vector and it tries to create the superposition of those in the qubits and to encode that data in the qubit state. And then there's this short depth variational circuit. So basically variational circuit is some circuit combination of gates and all. And basically the idea is we have to vary those parameters, the rotations and the gates. So that is done using a classical algorithm. Like I told, like we use the Cobila algorithm. So basically we get the loss function and we try to like reduce it. And then we measure it, we do the measurement as in any quantum algorithm. And then based on the measurement, we assign the label, whether it's a 0 or a 1. So yeah, so that's the algorithm in brief. So these are the some of the example feature maps and the variational classifiers we use. So we experimented on them. So this is on the top is the ZZ feature map. So it provides linear entanglement for the feature map. So for larger number of qubits, which we will do in future, it would be really like a good thing. It will be very powerful. And similarly, there's this variational classifier. Okay, so I will just show the demo video. So can you please play it?
Yeah, sure. So this is the drawing pad which we were talking about.
So as you can see, like the user just type 5 and then we run this code and it would run it in the simulator, or we could use a real backend quantum computer and it will predict it using those models. So these are kind of handpicked examples because the accuracy wasn't really high, but yeah, it was like with more time and training, we are sure that we can improve it a lot better. So yeah, thank you. So I guess that's it. Yeah.
Yeah. So we have some references at the end, and yeah, that concludes our session. So we'll just stop the share.
Wow, thank you. Such a great presentation exploring the intersection of quantum mechanics, quantum computing, and machine learning. So last but not least, we'll have the group who did the Q control challenge present on their solution.
Hi. So I did my my last 24 hours work on the quantum in the Q control challenge, which was designing a quantum control techniques to create high fidelity pulses. So currently, the existing problems on a quantum computer are high error rates due to noise from the environment. So in perspective, when we really look at a classical computer, a transistor usually makes one mistake every 1 billion years, while a qubit is bound to make a mistake every 0.001 seconds, which is quite a big difference in error rates. So now the existing problem really lies on how to make quantum computers with large number of qubits with a much lower error rate to really make any application work on it. So the biggest reason for this error rates is that the amount of noise which exists from the environment. So what is this noise from the environment? So for this specific challenge, these are the some of the noises which I was able to identify from the given challenge. Is that one is an unknown rabbi rate, which is a rabbi oscillation is a basic process used to manipulate qubits. So when you have an unknown rabbi rate, it disrupts the qubit's function. Another thing is the detuning error between the pulse and the superconducting qubit, and state preparation and measurement errors, which are called spam errors, which sometimes give you a false positive or true negatives. And then sudden signal changes won't really work well with the quantum computer, and amplitude errors when we're computing complex rabbi rates. And lastly, heat causes distortion of computing as qubits behave more uncertain in these higher states. Now, for this challenge, the problem statement was that given some quantum control techniques, we need to provide 2 pulses that implement a high fidelity NOT gate and a Hadamard gate on the qubit on the cloud. So the qubit in the cloud is basically modeled off a superconducting qubit, and now there is a pulse which is being which is a microwave which is generated to simulate the quantum gate to measure the states that the qubit exists at different times. So now here's a NOT gate and here's a Harriman gate. So in the most perfect ideal condition, a NOT gate should have zeros on 2 of these ends and e to the power of I theta over there, and that's a Harriman gate. Now, the initial example was given basically with, as you see the graph on the right here are pulses which is being emitted, and so when we're simulating the superconducting qubit, we found some limitations which mimic the actual environment of the qubit. So one is like limit for drive amplitudes, dephasing error, control line bandwidth limits, and a confusion matrix for all span errors. So when we simulated with the basic microwave pulse, this is the error. This is an ideal output that was generated. So here's the measured NOT gate over here, and this is the ideal NOT gate. Here's the measured Harriman gate, and here's the ideal Harriman gate. And we got a certain NOT gate error of 56.9%. And for the Harriman gate, the error came out to be 45.6%. And this is a really high error for any for the quantum computer. Now, the challenge here exactly was to actually figure out which quantum control approach would really reduce that error really down. And the challenge was deciding between the 3 known control approaches. One is the optimal control, is when we use it. We use optimal control when we have a detailed view of the system that we want to improve. Robust control is when we have a limited partial knowledge of the system to improve. And lastly, learning control, which we really don't need any information about the model, and rather we just test the model and we kind of build off on what to do next. So the path that I chose was optimal control. So in optimal control, I used a technique called crab optimization, which is chopped random bases. So what this technique actually really does is it takes linear combinations from a set of basis functions and reduces the dimensionality of the optimization. And then later it uses that, it adjusts the pulse to the exact parameter values with precision. So earlier, as you see, there was a 56% error for the NOT gate and a much higher error for the Harriman gate. And applying this technique really brought down the error rate to 16% for the NOT gate and 24% to the Harriman gate. And so this is basically the image for the pulse on how the pulse is being emitted over here. And another technique that I used was an overall band limited pulses. So what this technique really does is it optimizes the system by enforcing pulse bandwidths with filtering. So it essentially just creates filters which reduces dephasing noise. So think of it as like a filter which reduces light passing through is one way of thinking about it. So, but overall, the result that I got was that NOT gate error reduced to 12.5% and Harriman gate resulted to an 18.75% once applying this pulse. Now, the interesting thing is I've used both these techniques. So first I applied the crab technique and then I applied the second technique. And in fact, the problem was I didn't really reduce. My expectation was that I would be reducing the error rate, but it rather increased the error rates when I combined these pulses. So I essentially just added these pulses together and it really didn't make any difference, but it just increased the error slightly more. So overall, the conclusion is that the crab optimization technique can be scaled for a multi-qubit system due to its nature of linear combination, and a band limited pulses can be used for dephasing and amplitude errors. Yeah, thank you.
Wow, great presentation and findings on Q-Control's challenge. Wrapping up, I want to thank all of the presenters today for volunteering to share your projects. A lot of really interesting ideas were shared, and I genuinely hope that each of you continue with your project and continue on in the quantum computing field. The field needs your bright minds. More broadly, thank you to everyone who made this possible, the mentors, leaders of tutorials, organizers, contestants, and everyone who participated.